Yeah, so in today's session, what we'll go over is how to use Ray and DeepSpeed to train large neural networks. But before I get into the details of how to use Ray and DeepSpeed, I'll just give you a brief introduction of what DeepSpeed does and how Ray and DeepSpeed come together to enable training of large neural networks and why these two particular frameworks. So to get started, we mentioned in the last session as well, so Domino is a place where you can get all the tools and technologies that you need to use. Domino is an open-ended platform, so we don't restrict you in terms of using a particular tool or a framework. We enable you to bring in all the tools and frameworks that are best suited for your task at hand. So in this case, what we'll do is we'll use two particular frameworks, Ray and DeepSpeed, to enable training of large neural networks. So in the last session, what we went over was how to train neural networks efficiently. And the way we did that was by quantizing these networks and by also using adapters, which are typically known as PEFT or parameter efficient techniques. But if you take a look at the ecosystem in general, there seem to be two different trends and two different directions in which they are headed. So in one direction, you've got all the hyperscalers and big tech focusing on larger and larger models. So that's this chart on the left-hand side, where you can see that you've got models that have more than 1,000 billion parameters. At the same time, if you take a look at the leaderboards that people who are developing open source software are putting out, the size of the models is pretty small compared to the chart on the left-hand side. So in this case, you've got models that are 70 billion or so in size. Of late, I think the largest model is the Falcon 180B model, which is pretty good, but it's still an order of magnitude smaller than what you expect. So even though 70B, 180B might seem small, when you actually need to train these models or fine-tune these models, you would still need a lot of memory, a lot of GPU RAM to train these models. And typically what you would have access to are 16 GB cards or 24 GB cards. The A10s, A100s, they give you 40 GB and 80 GB, but that's still not enough to train these small neural nets as well. In order to train them, either you need to put together multiple GPU cards, which means spinning up instances that have multi GPUs in them, or splitting this training across multiple nodes that have multiple GPUs in them. And that's what we'll go over today, how to enable that. In the last session, what we also went over was quantization and parameter efficient techniques, but they have their own drawbacks as well. If you still want good quality, if you want to scale up even more, what you need to do is you need to train these neural networks in full precision, or maybe instead of 32-bit precision, 16-bit precision, but that still takes up a lot of memory. And we can do that. I mean, it's not a problem. If you want to do that, we can still do that. But there are use cases where you would still need to use 16-bit or 32-bit precision while training your neural nets. So with that, like I mentioned before, Domino gives you everything that you need to build these neural networks. So the first thing that Domino gives you is a range of compute resources that you can use. So in this case, we'll use Ray, but Domino also gives you the ability to use Spark. So if you're doing data processing, you've got large data sets that you need to convert into features, you can use Spark. If you want to do the same thing in a more Pythonic way, you can use Dask. If you want to do distributed training as well, you can use MPI as well. And you can share your Ray and MPI clusters as well if you need to. So that's pretty much what you need in terms of infrastructure. We've made it simple, so all you need to do is click a few buttons on the screen, and Domino takes care of all the underlying orchestration that needs to happen. These clusters are also ephemeral in nature, so you don't need to spin them up and keep them up running for the entire duration. You just spin them up when you need to. Once you're done with your work, you can shut them down. So coming to the concepts and techniques that we'll be using today, and what DeepSpeed offers. The first technique that folks use when training large neural networks and they have access to multiple GPUs is known as data parallelism. In the case of data parallelism, what happens is, let's say in this case, you've got 4 GPUs. What you do is you load one copy of the model on each of these GPUs, and you split your data set into multiple batches. You train your network across these 4 GPUs, and you synchronize the parameters that they have. So in this case, these colors represent different things. You've got the optimizer states, you've got the parameters, you've got the activations, which are these different colors. So the blue ones are the activations, the green ones are the optimizer states, and these orange ones are the parameters. So you can see that it takes up a lot of memory, and this might work for smaller sorts of neural networks, but when it comes to larger neural networks, this sort of training paradigm might not work. But DeepSpeed lets you do data parallelism out of the box if you need to, if you're working with smaller networks. So smaller networks like GPT-2 or Distal BERT type of models, all of them will fit into these sorts of techniques, and it works pretty well. DeepSpeed also offers you what's known as Zero. This stands for Zero Redundancy Optimization. In this case, what happens is, since your neural network is large, it's not able to fit onto multiple GPUs. What happens is DeepSpeed just shards and keeps the parameters and optimizer states that it needs. It does not store the other parameters that it's not using. So in this case, let's assume we have 4 GPUs. So like in the previous case, your data is split across 4 different partitions. And additionally, what happens is the model is also split across these partitions. And the way it is split is only the parameters that are required for the model that's on a particular GPU is stored with that GPU. The forward pass happens like you see over here. And once one piece of computation happens, the communication between these devices takes place. At the end of all the forward and backward passes on each of these devices, the activations, they are synchronized across all the 4 devices. So at the end of one forward and backward pass, each device will have one copy of this entire blue line. So it's not going to have just one segment of this blue line. It will have an entire line over here that's filled up with all the activations from all the other GPUs as well. So you might imagine that this is happening because these devices are able to communicate with each other, and DeepSpeed takes care of all that orchestration. You don't need to do anything extra. You just need to specify the GPUs that you're using. Behind the scenes, what DeepSpeed uses, it uses either CUDA-aware MPI. So you could run this on a GPU if you want to. If you don't have a GPU, you can still run training on a CPU. It's going to be slow if you run it on a CPU, but it's still possible. And it does this by using MPI-aware CUDA. If you don't have MPI-aware CUDA, you could use plain MPI on a plain MPI cluster, and that will just work on CPUs. If you don't have MPI, DeepSpeed also works with the NCCL backend or Nickel backend that NVIDIA offers, which is the equivalent of MPI that you'd get. So it works. It's more or less, you could say in some sense, platform agnostic. It works both on different hardware sorts of platforms as well. And you get this ability to run and train your neural networks across multiple instances. So that's DeepSpeed, and this is what's known as zero redundancy. So that pretty much is telling you that whatever is not needed for a particular device and shard, it doesn't store it. DeepSpeed also offers other savings as well. So you've got this thing called activation checkpointing. What happens in activation checkpointing is all the activations also are not stored. Only the activations that are required are stored, and once they are needed, they are recomputed again. It's not an issue though. This increases the computation time but the memory savings are much more beneficial compared to the savings that you would get from recomputing this again. So it's quite a preferable technique, and you should use it as well if you're working in a memory constrained environment. Typically, if you've got GPU cards with 16 GB RAM or 24 GB RAM, this is a good technique that you can use. The next thing is mixed precision training. So what this lets you do is it lets you train your model in 16-bit precision, and it works pretty well. You don't lose a lot of accuracy because you're just going from 32 bits to 16 bits. It also offers some compression out of the box. So you can it stores your results in a slightly, again, a quantized type of a format. And when you need those results, it decompresses them back again to the full precision, and you can train your network using that methodology as well. So there's a bunch of other savings that you get out of the box. Again, all of this, you don't need to write any code. It's all through either a config file, or you can keep a parameter in code, and it all works out of the box. DeepSpeed has done a lot of engineering behind the scenes so that you don't need to do any of that. All you need to do is read the documentation and set these parameters in your code or in a configuration file. So what I told you about DeepSpeed was just I was just scratching the surface. There are other bunch of optimizations that DeepSpeed also offers. So we went over 0DP, we went over 0R as well. What DeepSpeed gives you is also called offloading. This is particularly useful, and the way it offloads is if your GPU runs out of memory, it takes some of the parameters and offloads them off to the CPU. It also offers you the ability to offload to your storage as well. So if you've got like NVMe disk or storage, SSD storage, you can offload to that as well. So that's quite useful. It also offers you memory defragmentation on the fly. So this is making sure that all your data is close together, so it's not taking a lot of time in reading and writing. DeepSpeed also gives you a bunch of schedulers and optimizers out of the box. And if you're using DeepSpeed, it's recommended to use the DeepSpeed optimizers. They've got optimizers for CPU as well. So if you want to run this optimization on CPU, you can use, for example, the DeepSpeed CPU AdamW optimizer. And quantization is also available. DeepSpeed also has other methodologies which are more specific or more native to neural networks. So they've got things like the Megatron approach to training, where optimizations have been done to the transformer itself, where the attention blocks have been optimized so that computations for all these attention blocks happens in one place, and they're aggregated. So it gives you these sorts of techniques too out of the box. But more or less, data parallelism and 0R with offloading is what's most popularly used. Like I mentioned before, DeepSpeed, it uses MPI, or it can use the Nickel backend. Now, that's all DeepSpeed, what happens under the hood. But when you come to using it, mostly you would be doing your development in environment like PyTorch or the Hugging Face transformers. And DeepSpeed integrates with these libraries. DeepSpeed has been written in such a way so that it's plug and play, it's modular. So you could also put it into TensorFlow if you're using TensorFlow, but the DeepSpeed team hasn't implemented those interfaces. But the way that it's architected, there's nothing stopping you from incorporating it into any other training framework that you're using. The easiest, though, is to, of course, use it directly out of PyTorch or PyTorch Lightning or the Hugging Face transformers out of the box. The DeepSpeed team has also benchmarked this against different neural networks of different sizes. They've done it for very large neural networks. And theoretically, this scales to, billions and billions of parameters. So all we spoke about was training the models. DeepSpeed also offers inference as well. So it covers a lot of the whole LLM ops life cycle too. It covers training with all the optimizations that it gives, and it applies a bunch of them to inference too. So you can quantize your models, you can deploy them to different servers, and you can get good speed. It doesn't support all the architectures and all the neural nets that are out there, but coverage is pretty good and performance is pretty good too. So if you want to use it for inference, you can use it over there too. Now, if you were to compare the transformers library and what you would get with the DeepSpeed integration with the transformers library, the transformers library is built on PyTorch, and the DeepSpeed library, it uses Python behind the scenes. It integrates with PyTorch and other frameworks as well. So it gives you that flexibility. The transformers library, for its scaling, it uses the accelerate library, and that allows you to train across different GPUs. DeepSpeed offers more. It does what transformers does, and it has other techniques as well. It's got pipeline parallelism, it's got tensor parallelism, it's got a bunch of these other things as well. The other thing that DeepSpeed gives you is you don't need to bother about what sort of hardware you are using. You can scale to very large models without having to run a TPU or specialized hardware. So that's good. If you are already using an MPI cluster to do some other scientific computation, then you can reuse that for DeepSpeed as well. You don't need to spin up a different cluster. So you can share infrastructure as well, which is pretty neat. Of course, if you're not using MPI, you just want to use NVIDIA clusters, you can use the Nickel backend. So that was a bunch of background about how DeepSpeed works and what it offers out of the box. The way you'd set this up is via a configuration file, and DeepSpeed offers 3 levels of optimizations when it comes to zero. So you've got 0, 1, 0, 2, 0, 3, and each of these numbers pretty much stands for what you want to shard. So if you want to shard the optimizer states, the parameters, and the gradients, those are in increasing order of the numbers. So if you want the just the optimizer states, that's 1. If you want optimizer states plus parameters, that's 2, and so on. And the way you would specify this is through a configuration file. On the left-hand side, you can see these are the different keys that you'd need to that you'd give to the DeepSpeed optimizer. A lot of them, if you just set them to auto, you should be fine. So you've got things like gradient clipping. You can get it to choose the batch size as well automatically. But typically, you would run a few experiments to see what works well for you. But out of the box, auto works well as well. If you want to get more performance out, then go ahead and tweak these parameters. And all of this is fairly well documented on the site. You can take a look, but these are more or less the most important parameters that you would use. And more or less, depending on the hardware that you're using. So if you're using the later Ampere type of GPUs, then you'd enable BF16. Depending on the task you're doing, you'd choose your scheduler and the optimizer as well. You can play around with the optimizer. And the optimizer and scheduler, they have an effect on the accuracy and final results that you get. If you were to do this in code, this is how it would look. This might be a little small to read. We'll go through this code so you can get to see it better later. But it's more or less the same parameters. But what you're doing is, instead of setting it up in a configuration file, you set this up as a dictionary. And each of those parameters is just a key in the dictionary, and you can nest them as well. This code at the bottom is more or less how it integrates with the trainer and storing checkpoints and different things like that. You can also execute DeepSpeed from the CLI. So if you're running CI/CD type workflows, if you want to run this on a schedule job inside Domino or in any other pipeline tool, you can do that as well. You can execute this from the CLI. You just pass these CLIs as the CLI arguments, and those become the parameters that you saw in the dictionary or the config file earlier. The keys also, they match the same names that were specified earlier. DeepSpeed also has a dsconfig file that you can specify. So if you want to specify what GPUs you want to run on, if there's a whitelist, blacklist of those GPUs, if there are particular IP addresses of those GPUs that you need to specify, you can do all of this in this DeepSpeed JSON file as well. So quite a lot of flexibility out of the box in terms of how you want to run your DeepSpeed code, either CLI, the command line, or through code itself. So that was about DeepSpeed. But what DeepSpeed gives you was a lot of optimizations on the neural network training side. There was a little bit on the infrastructure side as well. But where Ray comes in and where Ray is useful is more or less in the orchestration. So if you want to scale up, if you want to scale up dynamically, if you want to have better orchestration between your data as well as your training, that's where Ray is more useful. And we offer ephemeral Ray out of the box, so you don't need to do anything extra. All you need to do is just choose what infra you need on your head nodes and your worker nodes in Ray, and you're good to go. You would typically be using different libraries when you're using Ray, and you can either set that up as libraries in your Domino environment, or you can do that at runtime as well. So Ray gives you this init function where you can pass in what libraries you want to install. It's recommended that you do it in a Domino environment, so that way there's reproducibility, auditability, all of those functionalities that you get out of the box with Domino. One thing to be careful about though when you're doing your development is try to pin the libraries that you're using, because some functionality might break, and these libraries are also getting updated quite frequently. So just to make sure that you can reproduce the results or you can pass it on to other folks, it's good to pin these versions. Here's a little bit more about how you set up Ray in Domino. Like I mentioned, it's all through the UI. So all you need to do is you need to choose the cluster. In this case, choose Ray. Domino comes with auto scaling out of the box. So what that means is you might, in this case, provision 8 nodes, but Ray will not spin up 8 nodes immediately. Only if your utilization hits 80% or so, it spins up another node. So that's better from a cost perspective. It's better from an efficiency perspective as well. When you are doing this in Domino, you typically need 2 different environments. One is one environment for your workspace. The other environment is for your cluster. So the workspace environment is pretty much where your IDE spins up and you'll write your code over there. The cluster environment is where the code actually gets run and executed. And you can also choose different hardware tiers that you want to use for both your workspace as well as for the head node and the worker nodes on your Ray cluster. Typically, the head node, you would make sure that it's sized so that all the data from the workers, if it's getting sent to the head node, it's able to handle and deal with that. Typically, in most cases, you only send the results. You don't really send all of the data back to the head node. And you can size that to be slightly smaller than the worker nodes. So in this case, we've chosen a hardware tier that's got 4 cores, 15 GB of RAM. The GPU is also, you can specify that in your hardware tier. The next thing is after you've provisioned your infrastructures, you'll start writing your code. That's also pretty easy to do in Domino. If you're doing local development, prototyping, you're not ready yet to spin up a Ray cluster and you just want to prototype your Ray code before spinning up a cluster, you can do that as well. Just call the ray.init method. It's not going to do any distribution or parallelization, but all the APIs, SDKs that you would use from Ray would you can still use them and just test out your code if it works. Once you're done with testing, you can actually go and spin up a cluster and run all of it. To do that, all you need to do is Domino pre-populates these environment variables out of the box, which are the host and port values. So you don't need to do anything. You just need to pass those host and port values to ray.init, and you'll have a cluster that's up and running. So this is how you do it if you want to set a working path and a working directory as well for Ray. Otherwise, it's just this Ray init. So that was about Ray and Domino. This is how all DeepSpeed, Ray, and Hugging Face come in together. So Ray offers this thing called Ray AIR, which stands for Ray AI Runtime. And this is more or less what offers the integration between Ray and Hugging Face. Hugging Face and DeepSpeed are integrated. So so through this, you get a chain of integration with Ray, Hugging Face, and DeepSpeed. So the way Ray integrates with Hugging Face is you have this transformers trainer. In this transformers trainer, you can specify the number of devices, the batch size, the number of epochs, all the different things that you would typically do during training. It also gives you this scaling configuration where you can specify the infrastructure that you need to use. You might want to size this differently from what you've spun up on your Ray cluster. If you don't need to, then you don't need to specify these values. It'll take in whatever's available to it. Ray also offers Ray datasets, which is a good bridge between all the feature engineering that you would have done and the distributed training that you need to run. So Ray has its own object store. It makes sure that all the data is available to all the nodes, all the communication is happening efficiently between the data that's required by all the nodes. So Ray has this thing called datasets. This works pretty much how you are used to using neural network development. You can split your data into train, test, evaluation, these splits, and then add pre-processing. Your pre-processing can be a chain, and you can pre-process your data here as well if you've not used a framework like Spark or Dask earlier. This is again how the entire code looks like. It's probably not too visible over here on screen, but we'll walk through this code. But it's as you can see, it all fits in a few lines of code in one particular function, and you're good to go. So this includes the DeepSpeed parameters, the Ray AIR trainer, and the Hugging Face training code. So if I'll walk you through the code of how this actually works in practice. But if you want to run this code on yourself, we have a GitHub repository. It's a public repository. You can go and access it. It's available at github.com, Domino Data Lab, and the reference project name. In this particular example, what we did is we took a GPT-J model. That's a 6 billion parameter model. And we used it for a style transfer task using Ray. We spun up around 32 GPUs, and it took less than 10 minutes to train this entire model. All of this happened in an ephemeral fashion, and I'll walk you through this code in a moment. So yeah, this is my Domino environment. So the way to set this up was, like I mentioned before, you need to have two environments, one for your cluster, one for your workspace. This is how my cluster environment looks like. So I'm pulling an image, a base image from Ray. It's got all the Ray dependencies installed in it. Additionally, I just install my libraries that I need. So I've got most of the Hugging Face libraries and PyTorch DeepSpeed over here. DeepSpeed is also just a pip install. You just need to specify the version of DeepSpeed and you're good to go. You don't need to do anything extra. So once this is up and ready, I can create a workspace. Like I mentioned before, the way you would create a workspace is choose the ID you want. And then If you click next, you can choose the cluster. You can choose whether you want to scale this cluster or not. In this case, let's choose 8 nodes. You can choose the worker hardware tier. If you want G5, this has got 8, 10 GPUs on it. You can choose that. You can choose something similar for your head node as well. And this comes out of the box, the cluster compute environment. This also one I had set up earlier too. You can use that. So yeah, I mean, once you're ready, you click launch and you'll have your Ray cluster up and running. So I've already done that. And this is how the code looks like. So like I mentioned earlier, these environment variables are already specified, already provided to you in Domino. All you need to do is specify, read it from the environment and give it to Ray init. And you'll have your model up and running. Here are some parameters that I've set up. If you want to change them, you can change them. You can use the defaults as well. So this is pretty much how Hugging Face, you would use this in Hugging Face. You specify the name of your model. There are some extra flags that I've set up over here, which is use GPUs if you need to. Yeah, I mean, not need to, if use GPUs for sure. Then I use the regular Hugging Face libraries to do all the data processing, loading the data. So in this case, there is a data set. It's Newton's principles of mathematics. So you can ask it things about mathematics and it'll answer questions to you in that style as well. And yeah, I pretty much load this as a data set dictionary. Once this is ready, we can pass that on to a Ray data set and create a Ray data set. So this can later on pass that on to the Ray workers that would do the processing. So Ray offers this functionality out of the box. You just need to call Ray data from Hugging Face and pass in the data set, and you're done. There are other parameters as well. So you've got a block size. You can play around with this if you want to. But yeah, I mean, it works equally well. If this more or less has to do with the sort of resources that you've allocated. The next is data processing. So I do a little bit of data processing over here. So this data set that I was actually using comes in one big batch. So what this does is it splits that into different pieces of text and processes and tokenizes that text. That's more or less what this code is doing over here. It's splitting the text and tokenizing the text. That will be used for training the model. So fairly easy. You've got these classes as well, batch mappers that you can use. So this will do it efficiently. It'll do it in a map. So you can think of that as some parallelized way of processing the data. Then this is the crux of the training code, where both Hugging Face and DeepSpeed will come together. And this integrates well with the entire Hugging Face ecosystem. So I'm using the evaluate library from Hugging Face, from using the transformers library from Hugging Face, and pretty much all the libraries that you would use if you're doing your large language model development in Hugging Face. The extra thing that we do over here is we import a Ray AIR session. This is more for logging all the parameters and doing a bunch of experiment management if you want to, and making sure that the checkpoints are getting logged as well. This function is more or less what Ray will execute on all the different nodes. And if you want, you can pass in extra variables to it. So if you're doing things on the CPU, you can pass in the number of OMP threads that you want to use. In this case, what we've done is we've allowed TF32 for the matrix multiplication operations. This is both for performance as well as for accuracy reasons. And you can set up all the parameters that you would use for neural network training over here as well, using this config. We'll pass in the batch size, epochs. These are defaults, these 4, 2, 0. in case they're not specified, these defaults will be used. Now, this is where the deep speed setup is happening. In this case, I'm setting it up as a dictionary in Python as opposed to a configuration file or running it from the CLI, because we'll be using Ray to execute this code. So these are the different deep speed parameters that I've used. I'm using BF16. I've said enable it auto, so I don't really need to worry about whether my infrastructure's got support for BF16 or not. Deep speed will figure that out for me. Similarly, with the learning rate, betas, all of that, I've set optimization as stage 3. So it's going to shard the optimizer states parameters and gradients for me. I've enabled CPU offloading as well. And I have also set gradient accumulation to be auto. You can play around with this as well. I'd recommend using gradient accumulation because that helps with saving a lot of memory saving. Otherwise, you might run into out of memory errors later on. So, yeah, I mean, there's no harm in setting it. And I've also set the micro batch size per GPU to be auto. So you can see a bunch of this just works well out of the box. You don't need to play around with it too much. The next thing that I do is I have training arguments. Whatever was in my config earlier, I passed them on to this training arguments. And over here, there's this parameter called deep speed, and the dictionary that we had set up earlier, we passed that over here to the training arguments. So everything's available to the training code, all the deep speed configuration. This is fairly standard code that you do using Hugging Face. We are just loading the tokenizer over here and the model. Once all of this is done, we set the metric that we need for evaluation. In this case, I've set up accuracy. We've got this compute metrics function as well, which converts the logits into actual probability values, and you can use that to make your predictions. And finally, this is the trainer, where everything is passed in together: the training arguments, the data set, the evaluation, the metrics that you want to compute, and the tokenizer. So this is preparing the trainer and returning the trainer. We've also set up a storage path over here. So all the checkpoints that Ray is being generated will come and get stored over here. In this case, we are using a Domino dataset because it's versioned, it's an immutable snapshot. So you get a bunch of that reproducibility out of the box if you store it in this location. Now, in this piece of code is the Ray trainer. And this is the transformers. This is where Ray integrates with the Hugging Face. And the function that we had defined earlier, which is this function, we just pass that over here to the trainer init per worker, which is more or less in initializing the trainer for each of the nodes that the Ray cluster will spin up. You can specify how you want to scale each of these, the training as well. So in this case, we are saying, yes, use a GPU. We specified the number of workers. We are saying if we want to specify a different number of CPUs that you want to specify for each of these workers, you can do that as well. Typically, you don't need to use a lot of CPUs, so you can choose a small number over here. And that's it. Specify the data set, specify a bunch of code that we had written earlier, and that's it. Called trainer.fit, and your entire code will run. The checkpoints will get stored in /mnt/datasets, and you're good to go. Once this training has happened, and if you want to make predictions on this training, all you need to do is load the model that was saved to the dataset earlier as a checkpoint and pass in data to that checkpoint. So that's what's happening over here. So Ray gives you a transformers predictor, which is how it's integrated with the Hugging Face. You load the checkpoint, you specify the kind of task you want to use, you specify the data type that we used. We'd set mixed, if you are using mixed precision, float 16 is good. You can use that. Device map auto, this splits it accordingly. If you've got multiple GPUs, it will split the model across these GPUs, and you can use that for your inference. And finally, call the prediction function with the prompts that you want answers for. These are the parameters that you typically set, whether you want to sample, the temperature that you want, depending on how creative you want your answers to be or not, the min and max lengths of your output. So you can take this predict function and incorporate it in either an API or an app that you're using, and you're good to go. So this is more or less how you would use this Ray, DeepSpeed, and Hugging Face in Domino, and you've got you can scale out of the pretty much horizontally to whatever extent you want, and all of this is enabled through simple code, all available through Python. You don't really need to do a lot of infra engineering behind the scenes. Ray, DeepSpeed, and Hugging Face do all of that for you pretty much out of the box. You don't need to wrangle with a lot of these issues. The thing that you might have to deal with is all the different parameters, and you can play around with them. If you want to use a sweeping search or a hyperparameter search for these things, you can do that as well. Ray also has some hyperparameter optimization tools that you can use to do that. These integrate also with different experiment management frameworks. So there are, in these training arguments over here, you can specify where you want to report to as well. Hugging Face also integrates with experiment management frameworks. So you can pass in those parameters too if you want to log these experiment results elsewhere. Yeah, so that was how this would work end to end, from loading your